So in the last lecture, we defined this joint distribution on SBM D comma lambda on, this is a joint distribution on graphs and communities. The joint distribution on X in, okay, yeah, plus minus 1 to the n, and graph G. Okay. And then we defined this distribution on X given G. This is, if I see the graph, I want to infer the communities by a Bayes rule, what's the distribution? And I said it's of the form so thanks. Yeah. So I said it's of the form some exponential of a quadratic function of X. Okay. Divided by Z, the normalization constant. And since I don't want to compute or talk about the normalization constant, I'll often write proportional to this. So when I say this proportional to, it just means that there's a normalization constant. The important thing is that it's e to the power a quadratic function of X. Okay. And what's the goal of this? What's the plan for this lecture? In this lecture, first, I will sketch the high-level ideas of the following claim that after, or let's say, suppose mu is like a 1 over n to the 4 locally stationary measure for the global dynamics on, for Glauber on phi, what will be true is that the expected correlation is at least a constant. Expected correlation with the true is at least a constant, assuming for lambda is sufficiently large. So this is the theorem, and I'm going to outline the proof of this theorem, only the very high level ideas of the proof, but there'll be interesting things to just understand there. And then I will move on to mentioning some of the favorite open questions on locally stationary measures. Okay, so but before we get into the proof of this theorem, I just want to talk about probability distributions that look like these. These are called Ising models. So Ising models will have a general notation for it. Mu J V, this is a probability distribution defined by a matrix J and a vector V. This is basically proportional to, let's say, summation Jij xi xj plus V dot x. So basically the quadratic function has, this is the quadratic degree 2 part of the function, and this is the linear part. And Ising models, are studied very extensively in statistical physics. And the point is, if you think of magnets, then if you have n magnets and the ith magnet is interacting with the jth magnet with an interaction strength Jij, and depending on whether Jij is plus or minus, the magnets try to be in the same direction or opposite direction. The magnets can be aligned in +1 or -1, 2 different directions. And so this is like the state of the system would be, this is the Boltzmann distribution for that energy. And so here, just to say, this J is called the interactions of this is the interaction matrix. Right, that is J, this is pairwise interactions. And this, the linear term, this is the degree 1 term, this is just some sort of external field, like local field, right? So basically for every, so if I look at this, v dot x is summation vi xi, right? So the vi is some sort of a field that's forcing the magnet to be in +1 or -1, it's biasing the magnet. So it's local fields and the interaction. And I guess the only important thing I want to say is that if you erase j, if j was 0, if I look at mu of 0 comma v, right, then there are no interactions. This distribution becomes a product distribution, right? And product distributions are nice. We understand them and they're kind of nice. So it's the interactions that make this complicated. Okay. So what do we know about global dynamics on this? So here's kind of one of the state-of-the-art theorems on global dynamics for this. This is due to Chan Eldon. They say that, let's say, suppose J is a PSD matrix. Suppose J is a matrix whose operator norm is less than half, meaning the largest eigenvalue is less than half in magnitude. Then global dynamics on mu JV mixes. Mixes to stationary, right? Mixes in, I think it's n log n time, n log n steps. So basically, of course, here I have to say J is positive semi-definite. If I have a Ising model where the interaction matrix has a small spectral norm, then the global dynamics actually mixes very well. Okay, and in fact, they show something called like a modified log-Sobolev inequality here, a function inequality or modified log-Sobolev inequality that actually gives you the mixing here. Okay, why am I saying this? I'm mentioning this is because now for us we have a Ising model, and we want to understand how well does this mix, how well does that mix. So let me okay. Actually, so let me write down the distribution gain. So actually, you know what? I need to say in my theorem statement, I shouldn't run global dynamics on pi. I should run global dynamics on sorry about this. It's okay. Let me just say what our Ising model is. So in our case, the distribution pi xg, this is our gold standard base rule. This is the gold standard distribution that we want to sample from. Okay, this I said is proportional to summation xi xj ij edge, right? But this is basically the adjacency matrix. So this is essentially mu sub beta times the adjacency matrix. Okay, where adjacency matrix of the graph, that's what this is. Okay, but you know, since the adjacency matrix, so it's a kind of a average degree D graph. It's not a D regular graph, but it has a very large eigenvalue because of the all ones vector. So let's get rid of that. Let's do, because it's a trivial eigenvector, so let's just look at this distribution instead. Okay, so I just took out the trivial eigenvector. Okay, so now if I look at remember our graph is a stochastic block model with just two communities. Okay, if I look at the adjacency matrix of this graph, you can think of it as having a large eigenvalue, which is the trivial eigenvector, plus another unusually large eigenvalue, which is coming because of the community, because the planted community, that's the most interesting eigenvalue, is the second eigenvalue. And then the rest of the matrix is much lower eigenvalue. It's think of it as random noise. So just to say this, well, basically this eigenvalue, we're not assuming the graph to be regular. Yeah, this is like a this is not an accurate picture. Yeah, these are not eigenvectors. These are like this. There is an eigenvalue which corresponds to the all ones vector, which is almost has eigenvalue d, right? So yeah, thanks. Yeah, so in fact, the annoying thing is when you actually sample this graph, there'll be vertices with degree log n. And so in some sense, there are very, very large eigenvalues, which are just there because of the large degree vertices. And so if you actually look at the proof, it's quite technical. You have to get rid of all the high degree vertices, and it's sort of annoying. But this is a caricature. I'm just saying, in some sense, the matrix, adjacency matrix of this graph has basically three components. There is the trivial eigenvector. There's the second eigenvector. This is the signal. This is really the signal. And this is the noise, as in this is the rest of the matrix. And the point is that the noise has small spectral norm. Right? This noise has eigenvalue, let's say root d. This lambda is probably much more than root d, and so on. Oh, in the noise matrix, yes, yeah. Yeah, you could do that. Yeah, that's right. So basically, okay, so in some sense, there are three components to this matrix. There's a d times 1 on trans, the trivial eigenvector, and then there's a second eigenvector, which is signal, and then there's a matrix of small spectral norm. Okay? Yes, yeah, right. Yeah, thanks. I want to use the same lambda as I did earlier. So the second eigenvalue is at least root d, yeah. Okay, so what does Chan and Eldon say? Chan and Eldon says that if you only had W, then it will mix. If I set beta to be 1 over root D, then if I only had W, then it would mix, right? So that's what it says, right? So mu sub W, which is, in this notation, mu sub W is the interaction matrix, then this mixes. Well, okay, so intuitively, there is just one annoying direction, which is in fact the most interesting signal direction, which is making this Markov chain not mix. Okay, so I'm just going to draw another picture here. This is again a caricature.
Scaling beta, so scaling now matters. You're somehow dealing with this at like 1 over d a.
So beta is 1 over root d. We know this, yeah. I mean, I'm like, we don't have a choice of beta in some sense, not much up to cost. That just comes from the Bayes rule, right? Because this is just apply Bayes rule. So beta will be 1 over root d, and you'll get the, yeah. So if you look at this situation, the situation is, in some sense, if this is r to the n, okay, and there is some direction v, okay, and you have the set of all x's. X's are what? Set of all x's are in plus minus 1 to the n, right? I'm going to pretend that x's are like continuous thing here. So if I look at the set of all x's, in some sense, like in directions orthogonal to this V, you mix. In directions orthogonal to V, you mix. That's what Chan and Eldan should tell us. So if this is my hypercube, these are all points in the hypercube, plus minus 1 to the n. And if I look at, let's say this is set of all level sets of v dot x equal to 0, v dot x equal to 1, v in a product x equal to 0, v in a product x equal to 1. So along the direction v, if I look at level sets, Chan and Eldan kind of crudely say that, well, the only reason you're not mixing is because of the direction v, right? The rest of the directions you mix. So intuitively, you would think that you're actually mixing on all these level sets. If I just restrict my attention to v dot x equal to some value, all the points with that, then you kind of mix there, but you're unable to mix along v. Right? If you didn't have v, if you just had working direction orthogonal to v, you would mix. Okay, that's what Chan and Eldan is telling us. So in particular, if you're stuck, what would the picture be? Intuitive picture would be that, well, you're stuck because like there is some bottleneck along V. In some sense, there is like, maybe you started on this side and you kind of mixed to these two slabs, but you're unable to cross this bottleneck to the other slabs, right? But on each of these slabs, you expect to mix fully. Okay. So this is a picture, and this is what we want to make precise. All right, and you would think that this sort of picture, it would be very, very tricky to make precise, but actually there is already a machinery developed in earlier works to do this. So here's a way to do it. So it's called restricted Gaussian dynamics, I guess. But basically, it's the following idea. So always in my explanation, X will be a sample from X will be a sample from plus minus 1 to the n, right? From whatever distribution. It could be locally stationary or whatever it is. So you can associate Z is V dot X, right? That's the level set, right? Plus, so the thing is that I could restrict X, I could restrict the distribution to one of these level sets exactly, but that is actually kind of very difficult to analyze. But it actually turns out to be very clean and nice to analyze the following random variable. Look at Z equal to V dot X, that's the correlation with the signal, plus an independent Gaussian noise. Okay, we'll see why this is useful, but this is an independent Gaussian noise. Okay, so if you give me X, then Z is this, right? So if you had a distribution mu, okay, then I can define mu sub Z to be the distribution mu conditioned on the value of Z. Right, this is mu was the original distribution. Okay, mu sub Z would be, I tell you, the distribution restricted to one of the level sets. That would be mu condition on Z. Z is just a correlation. But actually, I'm not telling you the correlation. I'm telling you the correlation with some Gaussian noise. But I can still define this. So in some sense, okay, basically, you have a way to decompose a measure. So given a measure, if you give me a measure mu on plus minus 1 to the n, all right? So you can define a random variable z, which is v dot x plus a Gaussian by root lambda, okay? And define the distribution mu sub z to be mu conditioned on this value. And then, of course, my original distribution will be some kind of average of these conditional measures. Z will be from some distribution, I don't know, some distribution rho, right? So, okay, basically if I didn't add Gaussian noise at all, let's just say I didn't add Gaussian noise, okay? Then mu sub z would be just the distribution restricted to one of these slabs, whichever slab. Z will tell you the slab number because z will be v dot x. Mu sub z would be distribution restricted to one of these slabs. And then, of course, the original distribution is a convex combination of those mu sub z's, right? Now, instead of telling you the slab number, I'm telling you the slab number with a noise added to it. But still, once I tell you z, there is some new distribution on x given z, right? And I can write the original distribution as convex combination of those. Does that make sense? Any questions on this? It's just a way to
Machinery makes sense, right? Is there a
yes, yeah, we'll, thanks, yeah, so let's, this, to make it very nice, let me say why this is nice, okay? Claim, here's a reason why this is nice. If I look at this mu sub z measures, it's actually proportional to alternately, this is basically the Ising model with interaction matrix W and lambda, a field which is lambda times V dot X. So lambda V, lambda Z V. So what do I mean here? You see that once I condition on the slab, this is what we expected. Once I tell you the slab number, the only the slab was defined so that if I fix a slab, the only interactions are W, because you're kind of fixing this eigenvector value in correlation with this eigenvector. The only eigenvector is W left, right? So, and what is this saying? This is saying indeed that's what happens here. You can write down the expression for mu sub z of x. That's just Bayes rule, right? I know the distribution of x. I don't know the distribution of z. I can apply Bayes rule. I'll get an expression which looks exactly like the interaction matrix you see is only W. The V is gone. The interactions don't have the top eigenvalue, the eigenvalue. It's only the original vector V comes in the field. It's an equality. This is an equality. This is an equality. Okay, so why? So
like the same is for every W of polynomial spectral norm that
it's not even spectral norm. It's just equality. It's just I'm going to show, but it's just a equality. Just calculating Bayes rule, you get exactly this. This now it's an identity. No, it is. Let's write down mu sub z of x. Okay, let's write down mu sub z of x. What is mu sub z of x? It's basically mu of x conditioned on, I told you z, right? I told you v dot x. That's what it is. Okay, what is this? This is proportional to mu of z comma x. right? The probability of Z and X, right? Okay, and you just write it down. So this is proportional to what? Well, the probability of X is what? Probability of X is proportional to that exponential of what we had earlier. X transpose Wx plus lambda V dot X whole square by 2. Okay, this is what probability of X was. And then Z, probability of Z is what? In Z, once I fix X, V dot X is fixed. It's only the Gaussian, right? The Gaussian's probability measure is what? E to the minus Z square over 2, right? So basically, this is plus Z minus V dot X whole square minus lambda times this. It's literally, I'm just writing down the Bayes rule. And when you write down the Bayes rule, the lambda VV transpose, this thing exactly cancels out. You only left with W. Oh, so mu is this. Okay, let me say what mu is. Yeah, sorry, I should say. Okay. Sorry. So mu W plus lambda VV transpose. Mu is this. It's an Ising model. Mu is an Ising model where you have lambda VV transpose plus W. Okay. Is that visible? Yeah. Okay, so mu is an Ising model with you have a W and another lambda VV transpose. Okay, and all I'm saying is if you define Z to be this, V dot X plus G over root lambda, then mu conditioned on Z, value of Z, has this form where the VV transpose term goes away.
He has a G component is very important. Right? If you didn't have that G component, you can section by alpha plane.
Right. Right. Yeah. If you didn't have this Gaussian noise, then mu conditioned on Z would be mu conditioned on just V dot X. You just get really hyperplanes, and you can't write down any expression for it. But here, this one is an Ising model. This one is and also it did exactly what we wanted to do. We wanted to get rid of that lambda VV transpose. It exactly did that. Right. So it's a very, very nice identity. And this is actually a special case of like a very general transform for Ising models called Hubbard-Stratonovich transform. Let me state that. The calculation is again very, very simple, but let me just state it here. So, let X be from mu JV, right? Mu JV. I've written JV definition here. I think I should have a half here. Sorry about that. So mu JV. Okay. Now define Z to be, any noisy version of X, X plus some C to the minus half G. C some PSD matrix. Let C be any PSD matrix. And it's some Gaussian noise. I just added some Gaussian noise. G is N01 to the N. So I have X from some Ising model. Z is like a noisy version of X. I've added Gaussian noise to it. Okay. And now I tell you Z. Now your distribution on X changes, right? You'd say, well, let mu sub Z be mu JV conditioned on the value of Z. If I tell you the value of Z, then your distribution changes. Okay, what is the expression for this? The expression for this is actually pretty nice. It is just mu J minus C, comma CZ plus H, CZ plus V. So the condition measure by an added random Gaussian noise, right? Gives you, it takes out exactly, I can pick C to be anything. Pick any C, I can take out C from the interaction matrix, right? For any C, I can take out C from the interaction matrix. In particular, for example, if J was PSD, let's say J is PSD, then I can set C to be J, which means I'll completely take out the interaction matrix. The resulting distribution will just be product distribution. So yes. And so, for example, if I set J equal to C, right, what happens to this? Mu sub Z will be this very simple distribution. The interaction matrix became 0, and this becomes JZ plus V, right? So, and of course, each of the distribution mu sub Z is a conditional, the original measure mu sub J conditioned on Z, right? Therefore, the original measure mu sub JV is actually an average over all of these, right? So, because, it's like, it's just conditioning, right? Yeah. So basically, I have some icing model. If I tell you the noisy, some sort of Gaussian noise added version of the sample, the conditional measure, after I tell you that, can become very simple. Like you can, depending on what kind of noise you add and what you do, you can, for example, make the interaction 0. The conditional measure is just an icing model with 0 interaction, product measure, and all those things. And therefore, you're expressing the original measure, mu JV, as a convex combination of these. Right? So you can express any icing model as a convex combination of product measures this way, and so on. But here, we're doing a particular incision. We are actually, we want to get rid of just this VV transpose term. Right? We want to get rid of just this VV transpose term. And so that's why we are using this choice of Z, right? And you get this. Yes. Yes. Slices. Yes. Yeah. You could. Correct. Exactly. Yeah. When I tell you the value of Z, you kind of your distribution is kind of smeared on a small number of slices. And the thing is that the resulting distribution is a nice icing model with, and it gets rid of exactly the VV transpose term that we wanted. Right? This icing model mixes, correct. That's the point. We chose this particular value of Z, this choice of Z, so that if I get rid of VV transpose, this icing model mixes. So therefore, in some sense, if you still want to keep this picture, for different values of C, we have decomposed the measure like this, so that in each of them, you mix. If you got a decomposition, when each of the components you mix. Okay, and questions so far? Okay, so this is good. Perfect. So because of this theorem, in each of those components, we mix. So, intuitively, if nu is a locally stationary measure, we actually think, okay, think of this as Z equal to 1, Z equal to 2, Z equal to N, think of it as different values of Z, and this is just mu sub Z. Okay, they're not disjoint, they're overlapping, but this is how it. And the thing is that if you think of a locally stationary measure, you know that in each of them you mix. Therefore, your locally stationary measure is going to completely occupy some of these blocks and not occupy some of the blocks, right? So for example, maybe you started at some point here, maybe it mixed here fully, maybe it went here, but it got stuck, right? So a locally stationary measure is sort of looks like this. That's our intuition. Okay, and we want to actually state that intuition. We want to state that intuition. So for that, you can define a different chain. The chain is called restricted Gaussian dynamics, which is basically it's a restricted Gaussian dynamics is the following. RGD is the following chain, right? Given X, I can get Z, which is V dot X plus Gaussian noise. Okay, and from Z, I can get another X prime, which is sampled from mu sub Z. Okay, so this X to X prime, this is the restricted Gaussian dynamics chain. It's basically the point is wherever you are, if you're in X, go find out which component you're in, go to uniformly random point in that component. Right, that's basically X. Let's say X is here, your X. Okay, find out Z, which means you'll find out which slice you're in, and you go to a uniformly random point in the X prime there. Okay, so so this is a new chain now. It's an RGD chain, right? It's taking very large steps. It's going, but the point is that if nu is locally stationary for the original global dynamics. Oh, thanks. Yeah, yeah. If nu is locally stationary for global dynamics, then nu is locally stationary for RGD. This is a claim. Yeah, this is a claim. So, I mean, this is exactly what we were saying, that since you mix completely in these components, and it's only across the components you're not moving. If you're stationary, if you're locally stationary, meaning you're stuck even on this RGD chain. What's the RGD chain? Start from X, you go to, you figure out which component you're in, and then you find the value of Z, and you go to a uniformly random point in that Z. This is black box. This is in fact, yeah, it's all black box application right now. Yeah, yeah. So far we're just in black box application of channel done, and it's yes. Mu restricted is, here I mean mu conditioned on Z, right? Yeah. Z itself is an indicator of the level set, right? Z is just V dot X. It's sort of the level set along direction V, and with some noise added in. Z is like a noisy reading of the level set number. V dot X would have been the level set number for X, right? And Z is like a noisy reading of that. And mu sub Z is given that noisy reading, what's your distribution on X? So it's sort of like, as Jay Kumar was saying, it's like once I tell you a noisy reading of the level set number, you're kind of the original distribution mu restricted to some of these slices. You know that it's, if I tell you the value of Z, you don't know V dot X, but you know that it's in some range. Yeah. And what we are saying here is just that because on each of these level sets, mu sub Z are mixing. If you have a locally stationary measure for global, you're actually locally stationary for this RGD, which is like a random walk, which jumps over a lot. Yeah.
One-dimensional chain. Not very, not get stuck by.
I think so. In general, like if you don't do anything, it's exponential because the graph actually looks like a dumbbell. So in fact, the graph has to look like a dumbbell because basically, so if I look at v dot x equal to 0, right? And v dot x, that's the middle. And then v dot x, it's symmetric across v dot x equal to 0. And close to here, it's very little mass. So, okay, so yeah, all right. So okay, so now we have a locally stationary measure that's locally stationary for this RGD chain, right? RGD chain. Now, now the point is that this RGD chain, as you can imagine, should be something simpler to analyze, right? Because it's really, in some sense, on these level sets. It's kind of a chain on the level sets. It is one-dimensional, right? So in particular, like, I'm saying the following: go from X to Z. Right, from every X, what does the RGD chain look like? Right, you have an n-dimensional vector. You map it to just a single number. And then from that number, you recover another n-dimensional vector. Right? And this number is basically, it's basically v dot x plus some Gaussian noise. Okay, so in some sense, imagine, you're running this chain again and again for many steps. The x's are going on some n-dimensional vector to n-dimensional vector, n-dimensional vector. But if you look at the z, it's going in one dimensions, right? It's walking in one dimensions. Right, z, from this you'll go to some z prime, which is, and then from that you'll go to x double prime and so on. That's the RGD chain. And what you're saying is the z is a chain in one dimension. It's like a noisy reading of the correlation v dot x. Right? So that's why you should expect that it should be simpler to think about this RGD chain than the original chain. Right? And yeah, RGD chain, yeah, you can't even implement it in some sense. Yeah, correct. Right. So the question is whether you can implement the RGD chain. I think I don't know, I haven't thought this through, but I think it's very tricky to implement RGD chain because this measure, although it's mixing, it's not easy to, it's not easy to run a Markov chain on. Okay. Okay, so all right, so this is an important fact. The important fact is if you look at the walk, it's going from an n-dimensional thing to a one-dimensional quantity to n-dimension to one dimension. If I look at just the one-dimensional iterates of this, right? This is like a walk in one dimension, right? And this is sort of reminiscent of, if you have seen AMP, as approximate message passing analysis and so on, they talk about one parameter recursion, the kind of getting one parameter, getting it down to one parameter. And that's what we have here for global dynamics in some sense, right? So, okay. All right, so let me just wrap up this outline. With how it proceeds next. is the following. So for this simpler RGD chain, we can actually show how the correlation evolves. It's called RGD boost, I guess. Sorry, I missed it. So suppose, suppose x dot v is R, okay? And then y is one step of the RGD chain. Okay, x dot v is the correlation, right? Correlation of x with the vector v. And I do one step of the RGD chain, you can show that the correlation increases. That's basically the key point. The correlation increases in one step of the RGD chain. So lots of this expression is kind of not super important for what I'm saying. So basically, if you start at a slice R, where the correlation with X with V is R, you take one step of the RGD chain, which is a much simpler chain, we can show that the correlation actually increases. How much does it increase to? It increases to lambda times R plus square root lambda times G, the absolute value of a Gaussian. Okay, but the key thing to remember is just think of it as lambda times R. Just for crudeness, just think of it as lambda times R. Remember, lambda is bigger than 1, right? So basically, you're getting some boost. You start with the correlation of R, you get large correlation. Of course, this increase in correlation plateaus out and at some point. But if your correlation is, let's say, very close to 0, it'll start increasing. So basically, if you look at v dot x is, let's say, 0. Your correlation of x with the true eigenvector was 0. In one step of RGD, your correlation will go up, right, and keep going up to until it plateaus. So that's what this is saying. This is just a statement about RGD. Okay. And then finally, this is good because if nu is locally stationary, yes, this is where lambda being bigger than, basically this lambda is bigger than 1. Yes, exactly. This lambda bigger than 1 is helping us increase the correlation, right? So if nu is locally stationary with respect to global dynamics, it's also locally stationary with respect to RGD, right? That's what we said just now, right? And that's good because then that just means that if you're locally stationary with respect to a Markov chain, I didn't state it. Basically, your measure is not moving. Your measure is not moving. It's got stuck somewhere. It's not moving, which means any quantity that you look at, its expectation is not changing, right? An expectation of any quantity should not change. That means that you can't have, for example, the correlation to increase. It should also already be stuck at high correlation, right? So meaning if mu is locally stationary with respect to RGD, of course, the correlation itself, it cannot increase in one step of RGD because it's, no quantity can change in one step. That's what locally stationarity is. So therefore, in one step, you'd have this property. If I look at this expected value, this should be the same as right in one step, the correlation can't increase. The expected value of the correlation should be basically the same. which means, you're already at good correlation, right? So basically any locally stationary measure will be at good correlation. It can't. Right.
This bottleneck comes a bit trivial in the sense that you're saying that I cannot change the direction of the correlation with B that easy. That's what this bottleneck in the chain is.
Mhm.
I cannot jump from B dot X being positive to negative that easy.
Correct.
But then there's a different bottleneck it seems.
Because it plateaus out.
Like, even when I find
Right. So let me actually say what should be the picture. The picture for, yeah. So here's the picture that you would crudely say is true for this distribution. Okay, so this is direction V. Okay, then you look at V dot X. V dot X equal to 0 is here, right? Your distribution should look like a dumbbell. This is how it should look. Basically, most points will have a particular value of correlation, and they'll be here. In fact, if you sample from the base distribution, you'll end up at this correlation. Either the correlation will be positive or negative, but it'll be some large value. V dot X will be some constant times omega n, some constant, let's call it base optimal correlation.
going to be the base of the condition on the sun.
That's the conjecture, yeah. It's a conjecture, you can't prove it, but this is the conjecture. This is what it should be. There's nothing else should be happening. The Markov chain should look like this. There's a big bottleneck in the middle, which means you can never get this exponential time bottleneck, probably. So therefore, you will never be able to get mixing here. But in some sense, you should be able to say that if I start here, I'll mix to this, this thing. Okay, what instead we are saying is, we defined this notion of locally stationarity, and then we said by all this work, we said that you have some sort of RGD boost, which means that if you're stuck with very low correlation, you kind of move out, right? Your correlation keeps increasing, right? So you kind of move out to the edges, right? And that's where you should be, and that's what this is saying. I mean, this is, I'm not qualified enough to make this conjecture, but this is the intuitive caricature with which I would. Right. Yeah. I mean, I don't really, yeah. I mean, this is the picture I work with when I think about this problem. That's probably the reason is basically because why is the picture should be one dimensional is because in some sense the matrix is right VV transpose lambda VV transpose plus W, and W has small spectral norm, and this is the only for small spectral norm you kind of mix. Oh, why is something special about 0? There's something that's special about this 0 is there's some sort of symmetry in that X and minus X are both the same because both lead you the graph with the same probability, same graph with the same probability. So that's why you can never distinguish X from minus X because it's just like renaming the communities from +1 to -1. So that's why this should be, yeah. Okay, so this is a very high level picture of how the proof goes, but I hope some of the ideas were clear. And the key, I guess one of the key tricks seems to be the ability to decompose a measure mu into simpler measures, right? And for Ising models, this kind of decomposition is possible by that Hubbard's Stratinovich transform. I think I messed up the name again. But this is a special case of that, where essentially I give you something about X with some Gaussian noise added. If you condition on that, the resulting measure is simpler. You can, if I pick the right kind of Gaussian noise, I can start taking out the interaction matrix, simplifying the interaction matrix. This is only for Ising models, degree 2 things you can do this. Okay, so this is a very high level outline of the technical thing of the proof, but let me use the rest of the time to actually I was planning to talk about some localization schemes, but I think that we might not have enough time for that. But instead, let me just step back a little and tell you some open questions. And okay, the first, I guess the one open question which sort of has brought, like was the reason why I started thinking about this a lot is to do base optimal recovery for stochastic block model, right? So you have a stochastic block model and you want to recover the community to the best possible correlation, right? Sorry, erase all of it. Okay, you want to recover the communities to the best possible value. What is the best possible value? The best possible value is basically if I sample for the correlation, best possible correlation is 1 over n. If I sample from the base distribution, from the conditional measure, then I get some correlation with the true communities. That's the best possible answer you can get. You couldn't do better than applying Bayes rule. And this would be the best possible correlation. Let me call it rho opt. Okay. And here's what you'd want to prove is you'd want to prove that global dynamics gets you this. Or locally stationary measures or global dynamics recovers to rho opt. Okay, this is good. Well, this is just one question you could ask. You could ask the same question for any other problem, right? You could, why do stochastic block model recovery? You could, as was pointed out, you could try to say, what about maximum independent set on degree D graph? Okay, or max cut on degree D graph. So max cut on random degree D graph. So, at a high level, all I'm asking is just running global dynamics to some point and getting stuck somewhere gives you a distribution or solutions which locally look like they're doing the right thing everywhere. If you stare at it, there's nowhere locally things are wrong. Every vertex is behaving based on if you just told me the neighborhood, every vertex is behaving the best way it could given the neighborhood. Right. So now let's say so basically locally you're doing the best possible thing. So then you could try to understand if this running global dynamics and getting stuck somewhere gives you optimal algorithms or some of these combinatorial optimization problems on random instances. On random instances, right? So right. So then so then the question is, okay, so how do you do it? I think I'm out, right? Okay, it's on. Okay, thanks. So, you could, how do you, you can't really solve exactly max cut because max cut is like the zero temperature version. So let's fix some very low temperature, but it's still constant above zero. Beta is some constant. Then you can just run global dynamics on that and get stuck somewhere and hope that where you got stuck is within epsilon of the true max cut value, right? And that's possible. I mean, basically, I'm just trying to say, for solving problems on random instances, um, running global dynamics and getting stuck somewhere seems like a useful algorithmic primitive. Correct. Correct. So correct. So, no, some of these are already solved, right? So max cut on random deregular graph, there is an algorithm that gets you close to optimal up to the second order in D. But okay, so my, okay, so, like, or, like for example, an all-time favorite long-standing question for me is, let's say I give you max cut on degree 4 graphs. Okay, worst case or random, doesn't matter. I mean, both are kind of known. Both are unknown. Worst case or random. Okay. How do you solve this optimally? What's the best algorithm for this? Okay. In the worst case, if I did not have the degree restriction, right, without degree restriction, worst case, SDP is optimal. Right, this is based on unique games conjecture, under unique games. Okay, so in some sense, you have an algorithm that does the right thing on high degree graphs or globally the right thing. When you come to low degree graphs, like degree 4 graph or degree 3 graph or degree D graphs, SDPs don't really seem to do the right thing. In fact, there's a whole different class of algorithms which have been heavily studied, which is belief propagation and approximate message passing, which are designed for low degree graphs, belief propagation. They've been analyzed for random instances, right? And so then if you want to figure out this sort of very high level question of what is the best algorithm to solve max cut on a low degree graph or CSPs, low degree CSPs, then one component is SDP. The other component has to be something hopefully something generic and composable. Something very generic and composable makes sense is, you run global dynamics for some time and you just stop somewhere. And we know that this distribution, after you run for some time and stop, it's doing the right thing locally everywhere, you can see. So why is it not giving the optimal max cut for these situations and so on? So anyways, that's a very vague, high-level question of trying to use this locally stationary measures to get algorithms, which are probably, hopefully optimal, even when, let's say, degree is 4, right? But let me say something more concrete. So let's forget about worst case, and let's just think about random instances. Okay. And let's even do stochastic block model. Let's say I want to solve stochastic block model to optimal correlation. Okay. If I have to solve it for optimal correlation, I need to understand what this optimal correlation is. What's the value of rho opt, right? And how is that proven? How do people extract the value of rho opt? Well, there is the way to extract it is there's a proof technique called the cavity method. The cavity method is, it's basically, it's a method from statistical physics, but, to say it in a very crude CS way, it's an inductive argument. Okay, what do you do? Well, the idea is just that. So I want to understand, for example, let's say pi sub g is the SBM graph. This is the pi sub g is the distribution on axis given g. Okay, for some SBM graph g. I want to understand what is the correlation of that with the true community. Okay, I want to compute rho opt. Well, what you do is you say, let me just delete this vertex v and look at pi sub g minus v. Okay, this is distribution on x for g minus v. Suppose I didn't have that vertex. Okay, if I didn't have that vertex, then I'll have probably another SBM graph, with n minus 1 vertices. The correlation shouldn't change. This rho opt shouldn't change. So in some sense, the correlation in G and G minus V are the same. But now, from the point of view of this vertex V, you can, things are simple. Because from this vertex V is just going to randomly connect to some roughly D of its neighbors in G minus V. And it's going to experience some sort of interaction with them, like those vertices would be, without in the absence of vertex V, the vertices, the neighbors, will have some marginal of being +1 or -1, and this vertex is just going to come and connect to that. This whole situation of what this vertex we experience is a constant sized calculation of probabilities. Basically, given what the neighbors are in the rest of the graph, the distribution of the neighbors are, the distribution of vertex V is determined by that. So basically, cavity method is, as I said, it's an inductive argument. You calculate rho opt on G minus V, I calculate rho opt on G. Starting from calculate rho opt on G minus V, so you get a recursive, you get a fixed point relation. In particular, it's an inductive argument. It only needs the following thing, If I look at the probability of a point X in G and G minus V, they are related by some very simple expression, which is just the neighbors of this vertex V. Okay, so the thing is that if you look at all of the Ising models or the distributions that come, Boltzmann distributions, the ratio of pi g to pi g minus v is simple because it's just removing one vertex, and this quantity is something very simple, right? And cavity method is just uses that fact to actually compute quantities like rho opt. Okay, and using that, you can, cavity method, you can actually show that rho opt comes from fixed point for some recursion and so on. Okay, so where is this going? We started the talk with saying that you can transfer proofs from stationary measure to locally stationary measure. So the thing that you would want to do is transfer cavity method proofs from stationary measure to locally stationary measure. Right, here's a general open question. Transfer cavity method proofs. So what does that even mean? Transfer cavity method proofs to locally stationary measure. The concrete statement I want to claim is the following. The concrete statement I want to claim is for every, let mu g and mu g minus v be locally stationary measures converged to, starting from the same starting point, converged to from x naught. Okay, so start from the same starting point and converge to some locally stationary measure. You would want to say that the ratio of probabilities here is exactly the same as the ratio of the probabilities for the stationary measure. That is this exponential of this beta times summation xv xu. with some epsilon error for most x's. The point is that the only thing the cavity method uses is it's the ratio of probabilities in the graph and graph with a vertex we removed is some value, right? You want to say that that's also true for a locally stationary measure, right? A graph with that vertex removed has this property. Okay.
Somewhere usually hidden in it is that often the side of the that the cavity that has or more than one thing, which both follow actually. Like there are two solutions to those equations, and then it's sort of built in that there are. So there at least to get this out of free, but it's not a local. It's like a.
No, but the thing is that this doesn't say anything about. That's why it's just the
Local similarity rather than.
Correct. Yeah. Okay, so let me state another. Okay, so this is like a slightly tricky question. Let me state a more concrete question, even more concrete question, which is, okay, so we want to show that on G and G minus V, if I run the walk, their ratio is certain probability, okay? But we don't even know anything about random walks in G and G minus V. So this is something even more simple. Let's take, let's say some random walk on G and G minus V. Let's even say global dynamics on SBMs, right? So the question is stability of random walks. Okay, so let's say take a graph G and you run global dynamics on G. Okay, and then global dynamics on G minus V. Or let's even just delete an edge or on G minus V. Do these two distributions, do these two algorithms produce samples which are even somewhat related to each other? Okay, so people use global dynamics even when things don't mix, right? The question is, how stable are those algorithms? Suppose I just delete a vertex or delete an edge, will the distribution entirely change? So in particular, yeah, okay, good question, good point. If you run global dynamics until it mixes, then this is sampling from stationary measure for G, this is sampling from stationary measure for G minus V, and they're within constant factors of each other because the e to the power, they're within constant factors of each other. Here I'm assuming that you're not mixing, so you're running for n to the 4 steps, or so for n to the 4 steps. Okay, so you would want to show that for any x, the probability that you'll sample in G x, and then you sample in G minus V, the same x, should be within a constant factor of each other, because you just removed one vertex in the graph, or let's say deleted one edge in the graph, right? Let's say you're sampling, and then in the graph G, you even deleted one edge. And the question is it true that the probability of sampling any particular x is within constant factors of each other? Or can removing an edge or adding a vertex, deleting a vertex, can it completely change the distribution of the outputs of the global dynamics? And this also has some privacy kind of implication, because let's say you're using global dynamics to sort of generate something, and then you want to know if that algorithm is sensitive to removing a vertex or adding an edge or deleting an edge, whether the algorithm, how sensitive it is. And I don't know how to even prove this fact, that if I just run on G and G minus V for n to the 4 steps, the distributions don't completely diverge to Even, for example, I don't even know why the statistical distance is like 1. Like what's the reason why the samples are not completely different in G and G minus 1? Oh, the starting point is the same. Yeah. Let's say you start from the same starting point. Yeah, you have a graph, you start from the same starting point, you run global dynamics, and you want to say that deleting a vertex doesn't change the samples too much. And we don't know how to do that. Well, let's say you run for n. I want to know, let's say you run for n to the 4 steps and yeah, well before mixing. Yeah, if we mix, we know this. We know this is true. Yeah. Yeah. I think any questions? I might stop a little early, but sorry about that.
I wanted to ask you earlier, do you expect to beat the greedy algorithm for finding independent sets in random? Like, do you expect Java dynamics
To do better than greedy.
Yeah, do you expect like
What is greedy?
common non-neighborhood and like just do
Local improvement, locals.
yeah. So I think about that. I discard all the neighbors.
For independent set.
Yeah, I'm thinking of click and translate. Click, I would say, take a vertex, this to its neighborhood, and then we know this gets you L log D by D in random. We know this. What about the ordering of? Like the ordering of the. Well, certainly doesn't matter because the graph is random, so the ordering can be fixed.
Okay.
But what I'm trying to understand is that we know that the optimal is factored too large.
Mm-hmm.
So there's a very simple algorithm, and I guess my question is: do you expect or imagine that locally stationary version of thermodynamics will be?
I don't know. I don't think. Maybe not. Yeah. I think what locally stationary things might give us is that if you just run a greedy algorithm or something, you will not be able to show that the answer is the right answer, it has the right constant, if the constant comes out of a cavity method or something from the belief propagation or something, right? For example, in stochastic block model, this is some strange constant which comes out of the cavity method. If we want any kind of crude algorithm to get that constant, it seems trickier as opposed to global dynamics and say, oh, it gets stuck. And so similarly, maybe for independent set, that constant is log d by d, and then there's nothing more you get.
The argument is like cavity method. It's like
yes. So, yeah, that's true. Yeah. All right. Yeah. Thank you.